Natural exponential function of base e, Naperian. Definition. Consider the natural logarithmic function g defined by ln x over 0 plus infinity, whose curve is c in an orthonormal system x prime o x, y prime o y. G is defined continuous and strictly increasing over 0 plus infinity. Then G admits an inverse function f whose domain of definition is the range of G, which is from minus infinity to plus infinity, whose representative curve is C prime. C prime is the symmetric of C with respect to y equals x. Now C is representing the function g, which is defined by g of x equal ln x over 0 plus infinity. It's defined continuous strictly increasing, which admits vertical asymptote, the y-axis. Then the inverse function f is represented by c prime, the symmetric of c with respect to y equals x, whose horizontal asymptote is the x-axis. C and C prime are symmetric with respect to y equals x. The explicit form of f. To find the explicit form of the natural exponential function, we have to start with the natural logarithmic function g of x equals ln x, y equals ln x. Replace x by y and y by x. Then we get x equals ln y. X can be multiplied by ln e since ln e is 1. Then, using the properties of the natural logarithmic function, we have ln e to the power x equals ln y, then y equals e to the power x. The natural exponential function of base e, or the exponential function of base e f, defined by f of x equals e to the power x over minus infinity plus infinity. Consequences of the definition. The domain of definition of f, where f of x equals e to the power x, is R from minus infinity to plus infinity, the interval from minus infinity to plus infinity. The second thing is very important. For any real number, e to the power x is always positive. If you go back to the graph of the natural exponential function, it's always above the x-axis. E power x is always positive. And you can think about it if you have a power 0, a power 1, power 2, even power negative number, you get a number which is always positive. The third consequence, e power 0 is always 1, e to the power 1 is 1, e to the power negative 1 is 1 over e. F, since it's the inverse function of the natural logarithmic function ln x, f and g have the same variation. Both are strictly increasing over negative infinity, positive infinity. Property number 1, a belongs to r, b belongs to r. We have two real numbers, any two real numbers. If we have the exponential power a times exponential power b, it's equal to exponential power a plus b. We are applying the rules of powers. The same base, we add the powers. These rules that you have encountered before in the middle school. E power a over e power b, division, the same base, e power a minus b. We have the same base, we subtract the powers. Pay attention, if we have e to the power negative a, it is the reciprocal of e to the power a. E to the power a to the power b. If we have power of a power, so we have to multiply the powers to base e. Here are some examples. You are applying the properties that we have discussed before. Property number 2, if we have e to the power ln x, it's equal to x, where x should be strictly positive because we have natural logarithmic function ln, so ln x, x should be positive. Oh, this property has a derivation from the composite function, but what we need is to know the property and apply it. The second one, ln e to the power x, so it is equals to x ln e. Ln e is 1, so it's equal to x for any real number. Why? Because e to the power x is always positive, so ln of a positive number always exists. Here you can see some examples applying the discussed properties before. Equations and inequalities. If we have any two real numbers, they may be also unknowns, e to the power a equal e to the power b, we can take ln on both sides, then a equal ln e equal b ln e. Then we can deduce directly that a equals to b. E to the power a greater than e to the power b, then a is greater than b. Even if we have e to the power a less than e to the power b, then a less than b. Here are some examples solving equations and inequalities. The second equation, we should have the same unknown, either e to the power x or e to the power negative x. We have multiplied both sides by e to the power x because e to the power x is always positive, so it will never change the equation. And we can change it to quadratic, solve the quadratic, then deduce the solutions. Derivative of the natural exponential function. The natural exponential function e to the power x defined over r has a very special derivative, which is itself. Now, e to the power x, we can have a function whose composite, yani the power x instead of x, we can have a polynomial or rational, irrational, whatever. So e to the power u, its derivative is u prime e to the power u. Here are some examples finding the derivative of the function. The first function, e to the power x squared plus 3x. So u is x squared plus 3x. U prime will be 2x plus 3 e to the power u. The second one is a rational function, so you have to take care that it's u over v. And it's u prime v minus v prime u over v squared. And you have to find the derivative. Now we can calculate the limits of the natural exponential function at a point or at plus or minus infinity, but what we are going to discuss here, limits at positive or negative infinity. Limit as x goes to negative infinity of e power x equals to 0. If you look back at the graph, so at minus infinity, the curve is tending towards the x-axis. And you can think of it e to the power negative infinity, so which is 1 over e to the power infinity, 1 over infinity tending to plus to 0. Limit as x goes to positive infinity of e power x. Also from the graph, as x gets bigger and bigger, the curve of e power x gets higher and higher. The e power x, it will be equal e to the power positive infinity, which is positive infinity. The third limit, as x goes to positive infinity, e to the power x over x, if you calculate this limit, then you're gonna have plus infinity over plus infinity. You can use L'Hopital rule, derivative of the numerator e to the power x over the derivative of the denominator, which is 1, and using the second limit, the answer will be plus infinity. The fourth limit, e to the power x over e to the power alpha, where alpha is a positive rational number. It could be alpha 1, 2, 3, even half, even 1 over 3. Then it will be tending to positive infinity using also L'Hopital rule. Limits as x goes to negative infinity, x e to the power x. If you calculate this limit, you're gonna have minus infinity times 0, which is an IF. Then limit as x goes to minus infinity, x over e to the power negative x. Do L'Hopital rule, calculate, then you're gonna get 0. Similarly, x power 1, x power 2, x power 3, where alpha is a positive rational number, this limit will be tending to 0. Now, the fourth limit and the fifth limit, we can say that the exponential e power x takes over the power of x power alpha for a quotient or a product. That means the answer will be depending on the answer of the limit, the calculation of the limit will be depending on the answer of limit as x goes to plus infinity of e power x, or x goes to minus infinity of e power x. Integration, integral e to the power x dx, it's e to the power x plus c. If you think what's the function whose derivative is e power x, is e power x itself. Integral e to the power ax plus b dx, so it's 1 over a e to the power ax plus b plus a constant. Integral u prime e to the power u, it's e to the power u plus a constant, and you are going to see some examples on this. Here are some examples of integration. The first one, integral e to the power 2x dx. You can multiply by 2 and outside the integral multiply by half. Then it will be half e to the power 2x plus c. The second one, you can consider u to be x squared plus 1. U prime, it's 2x e to the power x squared plus 1. U prime, integral u prime e to the power u, so it's e to the power x squared plus 1. The third one, we can use by parts, where we can have v as x plus 1, its derivative is 1, u prime is e power x, its antiderivative is e to the power x, then it's u times v minus integral e power x dx, and the answer is x plus 1 e to the power x minus e to the power x plus c. Here are some links that you can check to see more explanation on the natural exponential function, so you can watch YouTube to see more explanation. And I have already asked you to download GeoGebra applet regarding the exponential function, natural exponential function, that you can see the graph and the variations of the natural exponential function of base e to the power x. Thank you.